Right, so we move now into this massive field of calculus, which is very exciting, and you know it's going to sort of dominate our landscape really for certainly the rest of this term. But then it will feature in all the pretty much all the topics we do from this point on, vectors, probability, etc. excluded. Um, but it's a huge area of mathematics, and it studies the reason it's so big is because it's just so useful. It's so practical. Calculus is the mathematics of change. Now I'm I don't get too deep into this, but we live in a world where things change. There's no constant change. It's just not in reality what takes place. So the mathematics of change is an enormous area. So where we're looking at how to calculate rates of change and at different points in a dynamic that is where the relationship is changing all the time. So calculus looks at how we go about that. So just a few notes here just to kick things off. What we got right at the top here is differentiating from first principles. You'll see at the end of all this what that means. I'm not going to worry. Don't worry about that at the moment. Just take that down because it will make sense a bit later on. But certainly this part of the introduction, calculus is the mathematics of change. There are two types of calculus, differential and integral calculus, and like I said, these two areas are going to take us right up through to the end of term. Mostly differential calculus is a bigger section, partly because we are setting the whole thing up. Integral calculus, it's still a major area, and it's one that we'll spend a couple of weeks on right at the end of term. Hopefully we'll get to where we need to. Okay, so we're going to start with differential calculus, which is in chapter 7 of our textbooks, and the title of the chapter is limits and derivatives. Again, derivatives, well, we'll explain what that is, and limits and how they fall into this area will also be explained. Okay, so let's get started. What differential calculus does is it looks at change. Calculus looks at change. So change you can either have change can either be constant. Now I just referred to this. Constant change in the real world is not so prevalent. So we usually are looking at relationships where there is some kind of variable change. So but change can either be constant or non-constant. It's one or the other. If it's constant change, then what we're looking at is a linear relationship between two variables. So a constant change, if we want to measure constant change, so what this means is every time we increase this variable here by a unit, then this variable here increases by maybe half a unit. Every time we go across by 1 unit, it increases by half a unit. Some examples of that are driving at exactly the same speed. So maybe you're on cruise control, and but in reality, even with cruise control, nothing goes at the same pace. But you could look at some situations where you're buying tomatoes and they're $2 a kilo, and so if you buy 1 kilo, it's $2. That rate of change between the amount that you buy and the money you spend is a very simple very simple rate of change. It's constant, and it's $2 per kilo. There's not a lot of maths involved there. So calculus being the mathematics of change, yes, this constant change is still change, and so still doing mathematics on that is calculus, but it's trivial, it's basic, and it doesn't apply to most situations. But what we would do, and we know what this is called. This is a rate of change of y with respect to x. It's just the gradient. So to measure constant change, we are just measuring the gradient. So the gradient equals the rate of change here, and that's a theme that's going to run through, which equals just rise over run. So in our example here, it's just rise over run, 0.5. So that's for constant change, right? For non-constant change. So if it's not linear change, as in it's not always the same, then what do we got here? We're going to have a curve. So if we've got a curve, how do we measure the change? Because it's always the rate of change is by definition it's changing. So what do we do about that? Well, we've got a few options. what we can do is we can have a look at the average rate of change. So we can pick 2 points on this curve and go, let's have a look between this point here and this point here, and we can measure the average rate of change. We can draw a line between these 2 points called a secant, and we'll get back to that's a secant. A secant is a line that joins 2 points on a curve. You've heard, hopefully, as a little bit of pre-knowledge here for you, this is a secant or a chord, and this here touched at one point is a tangent. A tangent secant. All right, this is you don't really need to copy that down, but I need to explain. So this secant here. So what we could do is we could measure the gradient of that secant. So the average rate of change between, let's say this is all right, between A and B, these points. So the average rate of change, we could calculate that between 2 points, between A and B, is the gradient of the secant AB. So we could do that. We could get the points for A and B, and we can measure the gradient by using rise over run. That's an average rate of change, and we could do that. So we acknowledge that this is a this is changing. So the rate of change, and what we can see here with this curve, we just push it back this way a little bit, is that it's initially decreasing, it turns, and it starts to increase. But the rate of change is different at each point. At each point it's different. So we can pick 2 points and we can measure the average rate of change between those 2 points. Okay, that's something we could do. That's certainly a calculation of change. It's mathematics. And sorry, it's a calculation of change, and it's certainly mathematics, which falls under the banner of calculus. So that's doing calculus again. Pretty simple calculus and work that you will have done before. Anytime you looked at 2 points on a plane and used y2 minus y1 and x2 minus x1, that was what we're doing there. Nothing huge happening there. So that's the average rate of change. But right, what we want to get a little bit more involved in here is, well, okay, that's fine between 2 points, but what's actually the rate of change at a point, at a single point? At a single point, we want to measure the what's called the instantaneous rate of change. So let's ask that question. What is the instantaneous rate of change? So you can see which direction now we're going with with these questions, is that we're now going to, okay, I can do that. What's the instantaneous rate of change at a point? Let's say A. All right, what's the rate of change there? How is that measured? And this is where we now lead into this area of calculus. So what we firstly do is we say, right, the instantaneous rate of change at A. The first thing we need to do is define what that is. And the instantaneous rate of change at A is the gradient of the tangent at A. This tangent at A, that's the tangent at A. What is the instantaneous rate of change at A? Well, the answer, that's the question, the answer is the gradient of the tangent to the curve at A. That's the answer. So our attention and our efforts now turn towards finding out what the gradient of that tangent is. Okay, so let's with that in mind, let's now have a look at an example. Okay, so here's a little xy plane, and we'll just get y equals x squared up. So let's do that. Y equals x squared. There it is. Y equals x squared. So let's take the point, and it's not to scale. Don't worry about that too much. It's this is the point here. Let's take the point 3, 9. Okay, y equals x squared, 3, 9. And let's say we want to know what the so the aim, or the aim is here to find the instantaneous rate of change at the 0.39. Okay, so what we could do is we could say, righto, well, we could go to 416, go to another point, and we could put a secant down. All right, firstly, hang on, let's have a look at this tangent at 39. It's going to go through like this. So it's a pretty wobbly old tangent, but you get the idea. So the purple is the tangent. That's the goal. The purple is the holy grail. So to find the instantaneous rate of change at 39, that's the aim. So let's start on our path. We could just draw this little secant in here between 3 and 4. So we could find an average rate of change between x equals 3 and x equals 4. Okay, and that would be equal to, so what is it, 16 minus 9 over 4 minus 3. So that's what, 7. Okay, so the average rate of change is 7 between 3 and 4. But that's, you know, what we want. Look at our aim. We want the rate of change, or the gradient of the purple line. So how could we improve on that? Well, we could. What do you think? We could narrow down. We could shorten our secant up, couldn't we? So we could go in here, and you see if we bring this point down here from 4. What about we bring it back along the curve, really in close to 3, and so we find a little point in here somewhere and draw a little secant in there. Look at that little itty bitty thing, right? But if we find the gradient of that line, do you reckon it's going to be closer to the purple? Well, yeah, I reckon it is. The closer we get in, so let's do that. So we're still trying to find this instantaneous rate of change. So we're still finding an average rate of change, but let's say we go now, and we're going to average rate of change between x equals 3 and x equals 3.01. It's going to be closer, isn't it? So let's get those numbers. So at 3.01, right, we got 3.01, we got 9.0601, I think is what my calculation came, 9.0601. So that's going to be our little secant here. So average rate of change between 3 and 3. So now the rise is 0.0601, so 0.0601 over our run is now 0.01, 0.01. So what's that equal to? Dividing by 1 over 100, so that's times by, so it's 6.01. So now our average rate of change is gone down to 6.01. Now, do you think our average rate of change between 3.39 and 3.01, right, is closer? Right? And of course it is. The further this gets out, the further we're going to get away from our purple tangent. So that's better. It's certainly an improvement, but it's still an average rate of change. It's still only an approximation to our instantaneous rate of change at 3.9. So what we're doing now is we're sort of working in closer, aren't we? Working in closer. Right, now if we just think about, all right, let's see if we can improve this again. And now I'm going to take a different approach. I'm going to have a look now, and it's going to zoom in on this situation. All right, so here's my 0.39. All right, now I'm going to, all right, I don't want to draw that there. Okay, so this is my point. This is my point here, 3. All right, we'll go this 3.9. All right, but what I want to do is I want to take a point up here, but I'm not going to specify what it is. So I'm just going to say, let's go h along here. So let's not specify that we're going along 100th or 1000th or whatever it is. Let's just go h along there. All right, so what are my coordinates here? So my x coordinate is now 3 plus h, and my y coordinate, because this is still y equals x squared, my y coordinate is 3 plus h squared, which is 9 plus, what's that, 6h plus h squared, isn't it? That's my y coordinate. So now when I do my rise over run, I'm going to have, so if I look at my average rate of change now, so what am I doing here? Average rate of change, so just getting my zooming right, my average rate of change between x equals 3 and x equals 3 plus h. Right, let's have a look at this. What's that equal to? So it's now 9 plus 6h plus h squared over h. Sorry, that's minus 9, isn't it? So it's this minus 9 over 3 plus h minus 3, which is h. So what's this equal to? 9's cancel, I end up with 6h plus h squared over h. H is cancelled there, so I end up with 6 plus h. Right, so now this gradient here is equal to 6 plus h. But what's the goal here? What's the goal? The goal is to back this right down, isn't it? Keep going, keep going. So what's our value of h heading towards? It's heading towards 0. So as h gets towards 0, or ridiculously small, my rate of change, my gradient, heads towards 6. So we say it's equal to 6 as h tends towards 0. And so what we write that up as is therefore the limit as h tends towards 0 of my 9 plus 6h plus h squared minus 9, my original rise over run, right? Once I've worked it all out, the limiting value is equal to 6. And does that make sense from what we're doing up here? Sure it does. We're getting in closer. The closer we get in, went from 7 to 6.01. Now I'm saying, well, let's get right into 0. Well, there's our limit. So this 6 should be, and actually is, the gradient of my purple line. Okay, so that's the process by which we narrow down, and this is the first principles process of finding the derivative of a function, finding the instantaneous rate of change at a point. So I'm going to close the video there because I've gone on long enough, and I figure that's probably enough for one. There's still more to come with this, so I'll either put another video up or we'll talk about this in class tomorrow.